Hello, Taras here. Welcome to another episode of OSA TV, and today we're going to be talking about the sexiest subject I can think of. Today, we're talking about pH. pH is one of the most nuanced and kind of overly and underly complex concepts in both chemistry and especially in aquarium keeping when it comes to aquarium chemistry. So we're not going to get too nudged up in the weeds here, but for the most part, pH is a measure of the concentration of hydrogen ions. The more hydrogen ions you have, the lower pH. Less hydrogen ions you have, the higher the pH. Now, why do we give a rat's behind about that? Well, we care because that level of hydrogen ions, that concentration, dictates all kinds of biological and chemical activities. Everything from membrane fluidity, to the ability of an organism to take in fats, to regulate salts with its kidneys, everything. Everything is regulated by pH. It's kind of this context that wraps all of the aquarium chemistry that occurs in and outside the fish all in one. So today on OSA TV, we're going to be doing a worldwide tour of pHs, just to give you a little bit of an idea of what that scale really means, 0 to 14. I say 0 to 14, that sounds like nothing. I remember being in high school chemistry class and they told me 0 to 14, that sounded like nothing. It wasn't until I was able to work with all kinds of different organisms and learn about wild ecosystems that I learned that measure actually does mean something. And if we get a little bit of a rough metric for it, it can really help us in guiding our decision making in and outside the aquarium, before, during, and after maintenance. So we're going to start with the lowest of the pH, the highly acidic environments. And that really occurs in biofilters, in the deep, deep substrates underneath freshwater tanks, let's say. This is the area where you have lots of bacteria doing lots of different things. And for the most part, they are doing biological processes that require extremely low pHs, and their biological activity is driving that pH down. Our big general scheme for understanding pH is that biological activity makes hydrogen ions, drives the pH down. So things that have a huge concentration of microbes usually has a lower pH. Things that have a lot of geological influence, like lots of lava rock or lots of seashells or coral skeleton, that input rises the pH. We're talking about the super low pH, about 0 to 5, and that's all those microbes, and they're doing things like releasing organic acids, and we won't go through all the nitty-gritty details, but for the most part, their currency of energy are these electrons. That's their food, more or less. So they're manipulating these electrons and they're making a lot of hydrogen ions that way. So a lot of our molecular activity and microbial activity is at the very low pHs. Now let's kind of move up into something that we might care about a little bit more. Before we leave here, this is why it's so important to have media of certain chemical composition in your biofilter, like in a reef aquarium, for instance, or a saltwater aquarium. You'll have some sort of alkalinity so that low pH is constantly getting buffered by something. So let's move up. This is like the body of the freshwater tank itself. Planted freshwater tank is a great example of an acidic environment. Plants naturally like mildly acidic water, usually something in the realm of 6 to 6.5 to maybe the high 6s. And that's because the more acidic water is, the more nutrients like nitrates and phosphates become highly available to the plants so that they can absorb them. And it's also associated with all that microbial activity, which kind of drives and provides those nutrients in the first place. So the open water, freshwater planted aquarium really should be mildly acidic. And when we talk about fish that like acidic water, things like tetras from the Amazon River Basin and from the backwaters of these really, really productive river ecosystems, that's what we're trying to cater to. Something that has that lower acidity, that's what these fish want, that's what these plants want, so that they can have success. So now we're going to be traveling over to a little bit more of a neutral to basic pH, over here with the African cichlids. Now let's travel over to the African rift lakes. These are lakes which opened up when the continent of Africa kind of split open, and you had a little bit of salt water and a lot of geological interaction with the water that formed. So you had all this geological input. Remember, biological activity brings pH down, geological activity and the adding of buffers brings it up. So the African rift lakes are ecosystems defined by always having that geological input, and even though they're freshwater ecosystems with lots of biological activity that otherwise would drive that pH down, that input always keeps them at above 7. So that's why Things like cichlid lake salt are sold because a lot of these African rift lake cichlid species, for instance, like a higher pH of about 7.5, maybe even getting towards 8, because they really enjoy those higher levels. That's what they've evolved to adapt towards, and people will elevate those levels, not the salinity, they're elevating the pH so that those African cichlids are better catered to physiologically and are more apt to breed. The African rift lakes are a great example of this intermittent area where we still have fresh water, but we have a higher pH. Now let's travel to where we have a higher salinity and an even higher pH than in most African rift lakes. Now we're going to the coral reefs. Welcome to the open coral reef. Here is where we begin to enter the intermittent zone, heading towards even higher levels of pH. When we're in the estuarine areas that have a lot of freshwater influence, we're mingling with a pH of 8, rising up 8.2 and the like. But once we enter into the open reef, places where SPS corals will thrive, we have a much more stabilized pH, around 8.5, approaching towards 9. That's because we have the maximum level of geological input from all that open ocean water that's fluxing, and then we have a minimized level of biological activity. So this is an area where we really see stabilized pHs that are not really being swayed. We have a very stable environment, and that's why many of the SPS corals are highly dependent on stable and maintained pHs. Now we are in the pools that form after a volcanic eruption, where rainwater forms and is mingling with all this extremely molten and upturned volcanic and geological matter. This is where only very specific organisms like Agrospirulina platensis can live. Spirulina specializes in growing in these volcanic pools that can reach pHs of between 10 all the way towards 14. And it's because spirulina grows in these areas of extremely high pHs that they are able to actually incorporate all these really weird metals, copper, strontium, vanadium. All of these different metals are able to be incorporated into spirulina. Because of that, when you feed spirulina, dried or in a different form, to other organisms, it delivers all of those precious vitamins, minerals, and trace metals in a bioavailable form. So before we leave today, we'll talk a little bit about pH specifically in your aquarium. Generally speaking, geological presence, so having buffers, limestone, these things will raise the pH. Biological activity, having a biofilter running, having your fish breathe, poop, do anything, that will drive the pH down. In freshwater environments, pH is much more likely to swing. If you take lemon juice, which is very acidic, and put it in a swimming pool, that will sway the pH of the water as long as that swimming pool is fresh water. If the swimming pool is salt water, there are lots of buffers inside that salt that will prevent that pH from swinging. Now, why do we care about this? Many organisms, especially the generalist type that we tend to embrace in the aquarium trade, can handle a relatively wide range of pH within reason. However, many, if few of them, can handle abrupt, really short-term swings in pH. That can be highly problematic and cause a lot of stress, if not deadly stress. That's why it's so important not only to A, know the pH of your aquarium and plan appropriately, but B, when you're making adjustments to the aquarium, especially its pH, you have to be very, very gradual, especially when it comes to applying things like buffers and other things into a freshwater aquarium. You really want to make sure all of the changes that you make are extremely gradual, because it's not necessarily the level of the pH that you're at, the abrupt flux that could really cause lots of harm. pH is an extremely complicated subject, and I frankly have done a very bad job in even trying to generalize it. So if you have any questions about the pH in your tank and how it applies to the health and well-being of your fish, plants, invertebrates, corals, please feel free to come down here, talk to one of our many skilled and talented staff. Feel free to call our service line for consulting, and visit us at www.osachoice.com for all the buffers and other things you'll need to start observing and changing your pH.